Okay, hello everybody. I hope all of you are safe and sound and everything is going well with you. We start our first session in the course Energy Methods. In this chapter, chapter 1, we are going to speak about variational approaches. A variational approach is a mathematical way to find equations of motion for rigid bodies or deformable bodies and simultaneously find boundary conditions of the problem, and this is a benefit of a variational approach because we find equational of motions and boundary conditions in the same time using this method. In this chapter, we are going to speak about mathematical basics of a variational method, and in the next chapters we are going to talk about the application of this method to more practical examples such as equations of motion of rigid bodies or equations of motions of beams or bars and so on. Let's start our first lecture. In this slide, I'm going to speak about local minimum and local maximum of a function. You may be familiar with this concept from your previous courses, but as a review, I define local maximum and local minimum of a function and requirement of the function to be local extremum as total at specific point. For example, which conditions a function should have at a specific point to be a local maximum or to be a local minimum. Let's suppose that y equals to f of x, like here. Y is f of x, is a function of x. We define x1 local maximum of this function if be careful in this definition. Be careful on this definition. X1 is local maximum of function f if in an inadmissible neighborhood of x1, f of x1 is greater than f of x. x2 is local minimum of the function f if in admissible neighborhood of x2, f of x2 is less than f of x. This is the definition of local maximum and local minimum. We know from calculus that f dash a must be or f dash derivative of f with respect to x must be 0 in a local extremum of a function. Now I'm going to present a small proof of this statement. Let's assume an arbitrary point x equals to a, and write a Taylor series of function f about a position x equals to a. We can say that f of x equals to f of a plus df over dx x minus a plus 1 over 2 factorial second derivative of f with respect to x at point a, x minus a by 2, and so on. This is a Taylor series formula of f of x with respect to at position x equals to a. Now let's assume that let's rewrite the previous equation in the following form. If we took f minus r from right hand side to the left hand side, then we have this equation 2(1), f of x minus f of a equals to the right hand side of this equation. Okay, let's focus on these equations. If point A is a local minimum of the function f, then the left-hand side of this equation, let me draw a picture. You can see in this picture, if point A, we can say this is point A. If point A is a local minimum of the function f of x, we can say that f of x minus f of a always must be a positive number in order to point A be a local minimum. So for local minimum, the left hand side of this equation must be always a positive number. Okay, we use equals. We can say greater than or equals to 0. Okay, we know that this number must be a positive number. In the local neighborhood, we can say local neighborhood, for example, this is a local neighborhood, a very small neighborhood of point A, or an admissible neighborhood of point A. In this neighborhood, the left-hand side must be a positive number. Okay, now let's look at the right-hand side of this equation. If the left-hand side is a positive number, we can conclude that the right-hand side must be a positive number too. Okay, now let's look in the terms of the right-hand side of this equation. If x minus a is a small number, or x is close enough to the point A, we can say x minus a is very, very small number. We named it epsilon. Okay, if x minus a is epsilon, x minus a by 2 is epsilon by 2, and this term is epsilon by 3, and so on. If epsilon is small enough, we can say that epsilon is very bigger, or is very bigger than epsilon by 2, and epsilon by 2 is very bigger than epsilon by 3. So we can say that the sign of the left hand side is determined by the first term of the left-hand side of this equation or by this term. Okay, this is the thing that I want you to focus on this term, because as we can see, f dash a is has a specific sign. It can be a positive number or it can be a negative number if it's not zero. We can say f prime a is a negative number or is a positive number. However, x minus a, if x is greater than a, or if x is bigger than a, x minus a is positive. In this neighborhood, x minus a is positive. And if x is smaller than a, we can say, or in the left neighborhood, we can say that x minus a is a negative number. So x minus a changes its sign in the neighborhood of a, and in the same way, we can say that the left-hand side of this equation changes its sign in the neighborhood of a. And if we don't want this happen, we conclude that f dash a must be 0, or this number must equals to 0. So we proved that for a local extremum, f dash a, or the derivative of f with respect to x at x equals to a, or at point a, must be 0. Okay, and now, and if this term is equals to 0, then we conclude that the second term will be responsible for the sign of this equation in the neighborhood of point A. And in this term, we have epsilon by 2. This is always a positive number, and the term of the sign of this term will be defined by f double dash a. If f double dash a is a positive number, the point A is the local minimum, and if f double dash a is a negative number, the point A is local maximum. We all knew about this concept from your previous courses. However, I wanted to review this concept because we need it in our next slides. Okay, now let's speak about something new. Okay, till now we talk about how a function can have local extremum. Now we are going to define a new concept. We name it functional. What is functional? Functional, as you can see by its name, is a function of function. You can see here the simplest form of functional. As you can see, in this equation, we define functional I as a function of function y, where y is itself function of x. So we have function of function and we name it functional. Functional is a function of function or function of functions. In the simplest form of functional, we defined here. We define I equals to integral of f, capital F of x, y, and y dash d of dx from x1 to x2, from x1 to x2. And this is the definition of functional. Okay, and in the previous problem, we wanted to find an extremum point of a function. In this problem, we are going to find an extremum function of functional, or we are going to find undetermined function y in order to extremum, minimize or maximize functional I. Y is unknown. We know in many problems, not necessarily all of problems, in many problems we know the value of y at point x1 and the value of y at point x2, x1 y1 and x2 y2 are determined, but the curve between point 1 and point 2, if I draw it here, this is x-axis and this is y-axis. The point 1, let me change the color. Okay, and okay, now you can see better. The point 1 and the point 2 is determined. We are going to find the curve. There are many different curves from point 1 to point 2. We are going to find the curve or the unknown curve y equals to y equals to y of x in order to maximize or minimize the value of functional. This is our problem in variational approach. In variational approach, we are going to find the solution of this problem by finding ordinary differential by finding differential equations governing to y and by finding boundary conditions. In the next video, I'm going to speak about some classical applications of variational problem or functional problem, and you can find you can find more in our next video.